Welcome to the physics video lecture. This is Psci 168 video lecture 18. We are working on hydropower, and I'm going to attempt a little topic on hydropower, but the main goal today is again to send you out to look up a lot of pictures. So we'll start with this hydropower topic, and in fact we can always begin with our cartoon, to which we'll just keep adding elements, right? We have our dam, we have a lake behind the dam, and we have penstocks, power plant, and very important, the lower lake, because it's the elevation difference between those two lakes that determines the amount of potential energy. Okay, the elevation difference, H, of course we remember potential energy is simply M times G times H. So we've actually done some work along those lines. So there are two questions now. One of them has a really basic answer. The question is, how did the water get up here in the first place? Okay, there's our lake. How did the water get up there in the first place? And the obvious answer, better write down the question first. How did water enter the reservoir? Or how did water reach the reservoir? Because it's that potential energy, it's up there, it's above this lower level. And in our case that we're going to study today is way up in the mountain, so this H is considerable. Well, the obvious answer is the water cycle. And the water cycle assumes that we had evaporation, so we can let this lower level, in fact, you know, because of what we're doing today, we can even have a second powerhouse, and we'll just let this lowest water level here represent sea level. Sea level. So yeah, the water cycle is that water vapor is evaporated off the sea, and so we have to say what causes that evaporation. It's sunlight. So energy from the sun, and now we're going to have this water cycle. I'm going to cross everything I've just written. And what happens to the water in the water cycle? It does a number of things. It comes down as rain. It could actually come down as snow up in the mountains and then melt in the spring and flow down into the reservoir. Be that as it may, we have sunlight, so that is actually thermal energy. Radiant energy. That actually lifts all of that water up into the atmosphere. It falls down as precipitation. So you can see in this cartoon, we've just expanded it to include more of the whole energy world. We've got the sunlight, thermal energy we're going to have to talk about later. That's how the water got up there, so the water cycle. So that's an important aspect of the whole thing. But there's another way that the water can get up there. It can actually be pumped uphill, and that's the next topic. It's called pumped storage. So it's pumped uphill, and the reason for doing that is to store energy. This is the same thing as winding up our grandfather clock that we started off talking about. We pump water up the hill, it's now up there elevated, ready to be used. So that's our topic for the next few minutes. Pumped storage. Go ahead and just outline that, and of course I'm going to send you out into the world and find some good images for pumped storage. So this next topic here and it's very crucial to realize that the energy for pumping the water uphill has to come from somewhere. Okay? In our case, we have to think of it as coming from out of town somewhere. We have to think of it as being independent of this water cycle here. So somebody's producing excess energy, maybe 100 miles away, and the operators of, say, this powerhouse right here will purchase that energy. They'll use it, they'll run their pumps, actually they'll run their turbines backwards, so to speak, and they will literally pump the water up the hill. And how much energy does it take? Well, this much plus whatever inefficiencies are there. It takes the same amount of energy to pump it uphill as you can get for bringing it down. So pump storage, we'll say energy from an independent source is used to pump water up the hill. For example, there could be some gas-fired, coal-fired power plants that can't just be shut off and turned on with the flick of a switch. These are major operations, so the operators want to keep them running as steadily as possible, and when they produce excess energy, when the demand is low for their production, they sell that to our power plant up here, who's going to use that excess energy to pump water up the hill. Okay. So energy from an independent source, example, I'll just say gas-fired power plant. By the way, those are thermal power plants, one on thermal energy. We haven't really gotten there yet. We will. Okay, we're just going to take it into consideration. Gas-fired power plant has excess production simply because the demand isn't uniform throughout the day and night. So that excess production is sold or is directed to this power plant here, and that's used to pump the water up the hill. Excess production. And the point is, again, you can't just shut these gigantic machines off and on like a light switch. It takes time to run them down, fire them back up. And rather than do that, which is very inefficient, you keep them running and divert the energy somewhere else. So, excess production. Is directed to a pump storage operation. So I'm going to ask you guys to look up some good information on pumped storage, and I'm going to give you an example right now of a whole system in which this is in operation. It's local, it's in our backyard. You can get good images of it. And of course this is done all over the place, but we have a really good version of it right in our own backyard. Good, so let's see here. We'll stick with this cartoon. We've added the water cycle to it. We also, actually we have to add something else to it. So let's do that right now. So our power plant here, okay, here are some towers that carry energy away, okay? These are high voltage lines carrying it out to somewhere and bringing it in to here. So the power plant produces energy. We're going to learn about electricity later on in the semester, but yeah, it directs it on out. You can also buy the energy from out here, use it to pump water up the hill. So yeah, our cartoon has not only included the water cycle, but it's also included this external energy delivery and source. Good. We'll be drawing this more often than now. You know, we could also have the sun in here because sunlight, solar energy. It's all going to end up on our giant cartoon. Okay, so what I'm going to mention now and go through is the hydropower project on the North Fork of the Kings River. Okay. So here's where you want to start. Of course, you want to get images from that too, but North Fork of the Kings River. And I'm just going to put a list of objects up here that I want you to get images from, and you can get a good picture in your mind of what's going on here. So first of all, where is the North Fork of the Kings River located? Roughly speaking, we have the Central Valley and Fresno here. We have the Sierra Nevada mountain range. Over on the east side, we have Owens Valley. So you want to get a map out, or bring up a map on your screen and see you get Central Valley on this side, the mountain range, Owens Valley, and the desert ranges on this side here. To the east, okay, north, south, east, west, like that. And the north and the Courtright Reservoir, so the North Fork of the Kings River is going to be somewhere here. Now, Kings River is coming out from a couple of forks, and here's the North Fork. And right up here, there's a series of reservoirs and dams, okay? So North Fork of the Kings River. That's the first thing. See if you can orient yourself on a map, you know, the intermediate sized chunk of Central California. So what comes next is the system of reservoirs. You want to look up Courtright Reservoir. Okay, Courtright Reservoir, that'll be the upper one. It's at about 8,200 feet. Okay, Courtright Reservoir. And then through a system of aqueducts, canals, tunnels, penstocks, the water goes all the way from Courtright Reservoir down to Pine Flat Reservoir and to the Kings River below Pine Flat. Okay. So you'd have your last dam, and then you've got your Kings River down here emptying into the Central Valley. So I want to set up a list of these intermediate stages and objects that you guys go ahead and look up and get images for. But yeah, you need this first series of images just for orientation, and then you'll have the more local ones. Okay, so let's get this list going. Okay, so after Courtright Reservoir, which is the highest one, 8,200 feet. Put this right here. you have Wishon Reservoir. If memory serves, that's about 6,600 feet. 6,000, maybe 6,500, maybe a little more. Guys, check it out. Okay, you can find out these elevations. Now, the interesting thing here is that between these two reservoirs, there's a power plant right here, but these are the two that are used for pumped storage. So here we have power at this one here, okay, and then pumped storage. Okay, but we're still at roughly 6,500 feet of elevation. So what happens is the water from Wishon Reservoir is taken downstream through 5 or 10 mile long tunnels until they get to a penstock and drop into another reservoir. So I'm going to give you the name of that. You can look up Black Rock Reservoir. So 4, and this is just a small one, but it's enough to provide that lower level lake between the larger Wishon. So Black Rock Reservoir. And check the elevation. It's around 4,000 feet. And the, let's see, there are a couple of, yes. So there is the Haas penstock. So these penstocks, they're 1,500 foot sheer, or not sheer, but 1,500 foot direct drop down the mountainside. They're on the surface, they're big steel tubes, so you can get images of this. The Haas penstock, the Haas power plant is actually buried in the rock, not buried, but excavated in the solid granite somewhere around here. So you can get images of the Haas penstock. And then downstream again, after miles of tunnels through the granite, there's again a surface penstock just running down the mountain like this ruler here. And the one you want to look up is the Balch. So the Balch power plant, B-A-L-C-H. And also it's penstock. They're major construction projects to even run these 1,000, 2,000 foot tubes down the side of a granite mountain. So you've got the Balch power plant and penstock, and then you keep going some greater distance. Let's keep this list going here till they make it to the Kings River itself. So the Kings River powerhouse, as you follow downstream, Kings River powerhouse. But that itself isn't the, there's also a penstock here. If you look at these things through satellite view and zoom in, you can actually see all of these features. You can follow them downstream. If you just start up at Courtright, keep going downstream. So you got the Kings River powerhouse, and then there's one more. You've got Pine Flat Dam. Reservoir and powerhouse. And what you'll find if you look this up on the map is that the lowest level here is about 500, I found 572 feet. Okay, we're gonna have to convert all this to metric, right? But here's the point. We start up at 8,200 feet and end up at 572 feet, okay? And most of that is actual penstock height, because the tunnels that connect these various reservoirs are very nearly level, just slightly downgrade, So they use very little of this elevation difference. So roughly speaking, you would only subtract 200 or 300 feet of elevation difference from this total difference here to account for the sloping aqueducts. And almost all of this is going to be just direct, a vertical drop, as though this water were making a total drop of this many thousand feet. So let me formulate a homework. So we want images for as much of this as you can find, and put them together so a picture forms in your own mind of what's going on. That's why you definitely want to understand the location of the whole operation first. So that's the first part, just to reiterate. And then the elevation difference. Let's take, we're going to approximate here. Let's take 8,000 feet minus, let's say 600 feet, okay? So what do we get? 7,400 feet. Okay, what I want you to do is convert this to metric, convert to meters, convert to meters. Okay, that conversion to meters is what we can say, just to remind ourselves, how much potential energy does that water really have? Okay, so a cubic meter of water up there in Courtright Reservoir, which gets the whole thing started, would have its mass times G times an H of this, okay, converted to meters. Well, we can see already it's over 2,000 meters, okay? So it has an enormous amount of potential energy. This is a height that's about 10 times the height or more of Hoover Dam, okay, which is a pretty tall dam. So yeah, having the reservoirs in the mountains and making use of all that elevation difference is a really powerful thing. Okay, so yeah, homework. We want the images for this whole thing right here. We wanted specialized images about pumped storage, and then we want to convert this amount of feet to meters, because that letter H is this one right here in terms of potential energy. Okay, let me consult the clock. Yes. So like I said before, this is central to our whole discussion. We had that cartoon up there with the solar energy, with the out-of-town powerhouses, with the coal-fired, the gas-fired, all that stuff. So that's all going to come into play. Right now, though, we're in this center of the entire semester with our hydropower. And I want you to make a good effort to get a lot of these images, okay, and put them all into context. Yeah, so we're going to leave it at that. That's your assignment now I want to give you some time to really pursue this. Let me give you some resources for finding this. Okay, you've got that written down. Yeah, I'm going to go ahead and erase this. So some resources. Well, first of all, what you're probably going to do is just look up images, right? Image search. Say Google But maps, you can use Google Maps to great effect. I also like to use a program called hillmap.com, where there's a whole menu of different types of topographic maps that one can select for imaging things. You can just use screenshots. Once you locate something good, you can just take a screenshot and print it out. So hillmap.com has many topographic maps. And some of them will actually show quite a bit of the features that we're talking about in terms of the power plants here. So one really detailed one is, for example, Cal Topo Forest Service. But people are going to find different things, and that's part of the interesting nature of this. People do different searches and find different kind of pictures, so I'm not insisting on any particular one. But if you go through this list here, okay, systematically, first you orient yourself, then you go through all this list here, all the way when we have Pine Flat Dam. That'll take you through a major journey of the whole hydropower project. And as far as our formulas go, well, we don't need much more than this. This and the power formula and a little bit that goes along with it is enough for us to have a good grasp of what's going on. Okay, at this point I'll leave you to find all these things. See you next time.